All right, guys, we are back talking about method 160.1, spaghetti water. Well, no, not really, not spaghetti water, but I use that as an analogy. So things are dissolved in a water sample. I might not see them, but they're there. And then I'm going to filter that water sample. And the stuff that I'm collecting once it goes through the filter, that is the sample that we are getting ready to evaporate. So all the water evaporates off, and then we're left with residue that is left behind, and that residue is the filterable residue that made its way through. So how much stuff is actually there? Because is that contamination? Well, we can kind of almost deem it as contamination if, in fact, it is supposed to be very clean water. But it might just be completely harmless, like NaCl or salt dissolved in water. Whatever the case that is, they're wanting the TSS number or TDS number for a reason, and that's what we're providing. So TDS is what this is all about, total dissolved solids. All right, so section 7 is the procedure, and this is where we left off in the last video. So 7.1 says, preparation of the glass fiber filter disc. Place the disc on the membrane filter, insert into bottom of a suitable Gooch crucible. While the vacuum is applied, wash the disc with 3 successive 20 ml volumes of distilled water. Remove all traces of water by continuing to apply the vacuum after the water has passed through, and discard the washings. All right. So what this means is that I'm going to get a filter paper, and this filter paper could actually be contaminated. Oh no, contaminated, dirty, filthy, trashy paper. Yeah, that's right. So the purpose of 7.1 is to use some water in order to rinse the paper off. That's what this is all about. So we're going to rinse the paper off to make sure that all of that residue is gone. And it tells me we're going to do multiple portions of 20 milliliters. Now, this 20 milliliters does not have to be exact. This is just an estimate. And if I can use a graduated cylinder to measure those out, that is great. I mean, nothing else really needs to be done. I don't need to be volumetrically pipetting this. That is like too accurate for what we need. But a graduated cylinder will do a pretty good job for us. And it says 3. So that means in a SOP that a company would write, I need to make sure that that is included. So when I write an SOP for someone, I'm going to have to say, listen, the method says 3 times. You are going to have to do this 3 times. You don't do it once and pretend you did it 3 times. You do it 3 times because that is a requirement. If you don't do it 3 times, you violate the method. And if you violate the method, which in fact is our SOP, then you are not following the directions as they're written, and you invalidate the results. And that means all the work and all the money we've paid you to do that work is now for nothing. So thank you for nothing, and off with her head. No, they just get rid of you. All right, so 3 successive 20 milliliter volumes of distilled water. And then it just says apply the vacuum. So like there's going to be some residual water that's left over in that filter paper. If you keep that vacuum on, the purpose of that vacuum is to completely pull out as much water as it can. So if you leave the vacuum running for a little bit, it can help dry that paper out much faster. You know, it's kind of like the spin cycle of your washing machine. I mean, if you put wet clothes in a washing machine or after they wash and after they rinse, well, you don't just immediately take those from the rinse cycle into the dryer. They're going to be quite heavy. They're going to be soaked with water. So a spin cycle happens, and the spin cycle gets rid of all of that residual water in your clothing. So that way, when they go into your dryer, they're not as wet, they're not as heavy, and they'll dry a little bit better and a little bit faster. That is the purpose of keeping the vacuum applied at the end of this filtration step. All right. 7.2 says preparation of the evaporating dishes. If volatile residue is also to be measured, clean the dish to 550 degrees plus or minus 50 degrees Celsius for 1 hour in a muffle furnace. If only filterable residue is to be measured, heat the clean dish to 180 degrees plus or minus 2 for 1 hour. That's right, for 1 hour. Cool in a desiccator and store until it's needed. So there is a chance that this might have been done for you already. So we hope that it has been done. This is cleaning that evaporating dish that you're getting ready to use for the lab method. So what's happening here is that, just like the filter paper, we can't guarantee that those dishes are going to be clean as well. So in order to make sure that they are clean, then what we're doing is that we're placing these in an oven, and we're heating those at 180 for an entire hour to get them hot, to drive off anything that might be present. And then we are placing those crucibles into, or evaporating dishes, I keep saying crucibles, into the evaporating dishes, into the desiccator to keep them dry. So that way they do not absorb water again from the atmosphere or from the environment that you're working in. So it says cool them in a desiccator until they are needed, and then weigh them immediately before use. So we try to pre-clean these already. The time that you walk into the lab, this is already going to be done for you. These dishes are going to be in a desiccator. They're going to be ready to go. So that way you can just kind of grab one. But when I say grab one, be careful. Because you need to make sure that you wear gloves, and the reason is because you are dirty, filthy, trashy animals. That's right. All your fingers are greasy, your fingers are dirty, you probably had lunch, or you've been snacking, or you've been eating, or you've been digging, or you've been rubbing. Who knows what you've been digging and rubbing, but your fingers are quite filthy. Even if you wash them, they're going to be quite filthy. And I don't want your finger grease all over the dishes, because all of those greases and all of that contamination that comes from you, that is going to be transferred to the dish, and that's going to be extra weight, and that will give us an invalid result, because it is not just residue now, it's residue plus all of your dirty and filthy and nastiness. So we don't want that to happen. So I'm going to say, please wear gloves, and please limit your contact with the dishes as much as possible, because anytime you're handling and anytime you're kind of doing stuff with these, you have the chance of transferring all of that stuff over to those dishes. 7.3 says assemble the filtering apparatus and begin suction. So shake the sample and rapidly transfer 100 milliliters to the funnel by means of a graduated cylinder. So notice, again, it's graduated cylinder. That is completely close enough. I mean, we don't need volumetric pipetting here. That is perfectly fine, but a graduated cylinder is specifically said. So if I used a beaker, that beaker is not in the method. That beaker invalidates the method. I need a graduated cylinder because it tells me graduated cylinder. That is how specific these methods might be sometimes, and I have to make sure that I am following this to a T. So I'm going to take a graduated cylinder, that is a 100 ml graduated cylinder, and then I'm going to pour my shaken up water sample into that 100 ml graduated cylinder till I get to the 100 ml mark. Then I'm going to take that sample and I'm going to quickly pour it through that filtration setup. And that filtration setup that I'm using has that filter paper that is a glass fiber filter inside, so that way it catches all the big, large, chunky stuff, and it only allows water and all of the dissolved stuff to go through. 7.4 says filter the sample through the filter, rinse it with 3 10 milliliter portions of distilled water, and continue to apply the vacuum for 3 minutes. All right, so let's talk about this step. I've got 100 mils of sample that I have just poured through, and that sample is now all the way through. I've got nothing left, and I've poured it quickly, and the reason for that, I don't want stuff to settle in the bottom of the graduated cylinders. So I want to make sure that this stuff, when I've shaken it up and it kind of evenly distributes again, I want to make sure that I quickly dump it so that way all of that goes over. Otherwise, it's going to settle to the bottom, and sometimes it's a little harder to get out. So I just don't want to take that risk. So it says filter the sample through the filter and rinse with 10 ml portions of distilled water. So distilled water actually should be very clean water, right? Distilled water is actually cleaner than deionized water. Deionized water just means it's the removal of ions. And distilled water is actually the removal of ions plus other stuff. And that could be like things like microbes and bacteria and that kind of stuff. All right, well, distilled water should be clean. It should not have any type of residue that will be present. If I did distilled water in this test, I should be getting hopefully 0 for a residue number. There shouldn't be anything there. It's just like reverse osmosis water. If I did reverse osmosis, there should not be anything there. All of that water will evaporate and there is no residue left behind because there was nothing dissolved in it. It was straight up H2O. So in a weird way, it seems like we are adding to the contamination with these rinses, but folks, we are not. And the reason is because they shouldn't have anything in the first place. That is why we're using them in order to rinse. So that means no tap water can be used because tap water has contamination. That contamination is going to fall through, and that contamination is going to end up being in that evaporating dish, and it's going to add to the residue numbers, and I can't allow that to happen. So again, be very, very particular with the water source that you use. This should not be an issue if you've been around in a lab for a while because it's like, use deionized water, use deionized water, use deionized water. Okay, well, deionized water we just kind of deal with. We don't have a proper distillery in the lab at this moment. But at the same time, folks, we do have a ultra pure water system that is arriving at any point in time. And depending on the year that you're taking this class, we might have that water system in place, and we might be using that instead of our deionized water because that ultra pure water is just that. It is ultra pure, and it should just be H2O only, and we don't have to worry about these problems. And if that's the case, we'll let you know. But until that time, we're going to be using deionized water for the rinsing. Also, I will encourage you, it doesn't specifically say this in a method, but this graduated cylinder, there could be some residue that's left behind. So I would actually take the 10 milliliters of that water and I would add it into this graduated cylinder and I would swirl it around and then I would dump it onto the filter paper. So not only rinse your filter paper, but you're also rinsing the graduated cylinder that had your sample contained within it. That way you are ensuring that you are getting all of that dissolved residue as much as possible inside of that filter. And if you forget to rinse that graduated cylinder, there is a chance that you leave stuff behind. So I'm going to add 10 mils, swirl and dump, and then add another 10 mils, swirl and dump, and then add another 10 mils, swirl and dump. So you are ensuring that proper transfer is taking place here. It also says apply vacuum for 3 minutes. So don't be surprised if your SOP, when you do this, will ask you to write down the times that you're doing things. And the reason is because these times are specifically stated in some of these methods. And if they are stated, then it is a very good idea for the laboratory to include timestamps. Like, when did you start? When did you get to this point? When did you allow the vacuum to continue to suck through? When did you stop the filtration? Because that is a way that we can track the times that you are devoting to certain parts of these procedural steps. And the reason for that is not to drive you crazy, but the reason for that is because it's in the method. So don't be surprised if they want to know that detail, and that is why. 7.5 says transfer 100 mils or a larger volume of the filtrate to a weighed evaporating dish and evaporate to dryness on a steam bath. Okay. So I'm going to take my steam bath that we talked about in the last video. I'm going to place my evaporating dish above it, so that way I can heat and drive off water. And I'm going to evaporate to dryness on a steam bath. That means all of the water should slightly be gone at this moment. And then 7.6 says dry the evaporated sample. Evaporated, hello! Evaporated means no water left behind, so no water should be there at this moment. So dry the evaporated sample for at least 1 hour. 1 hour at 180 degrees plus or minus 2 degrees Celsius. After that 1 hour, again, time is very important. So I might be recording when it started, I might be recording when it stopped, and so forth. Cool it in a desiccator. That way it doesn't gain any water moisture back. And then weigh it. Then it says repeat it until a constant weight is obtained, or until the weight loss is less than 0.5 milligrams. All right, so let's do this again. 0.5 milligrams. Millis 1,000, 3 zeros, right? So move the decimal to the left 3 times. All right, so here's my first move, boop, and there's my second move, boop, and there's my third move, right there. So that means that ideally what would happen in a real world type of situation, and of course we don't have time for this, folks, but in a real life situation, what would go on is that after that 1 hour of heating, I'm going to take it out, I'm going to put it in a desiccator, I'm going to cool it down, and then I'm going to take a mass. And then immediately, ding, ding, it's like WWF, you go in for round number 2, or boxing match, you go in for round number 2. Round number 2, that means I'm going to heat it again for another hour, and then I take it out, I put it in a desiccator, and then I cool it, and then I take another mass. If my mass is different than 0.0005, so if it fluctuates and if it changes and the difference between those two masses are larger than that number, then guess what? Ding, ding! I go in for round number 3. I heat it for another hour. I let it cool. I put it back in a desiccator. And then I take it out. I mass it. And then I compare that mass to round number 2's mass. And if that mass is going to be greater than 0.0005 difference, gram-wise, then guess what? Ding, ding! Round number 4. And then ding, ding! Round number 5. And then ding, ding! Round number 6. So we don't have time to go through all of these heating stages in our academic setting, but that is a thing that you have to do in real life. Now, you might be lucky. You might be lucky and you might get it on round number 2. If you go to round number 2 and you heat it for the second time and then you put it in a desiccator and let it cool, and then you take a mass and that mass is less than 0.0005 difference, then celebrate! It's a good day. I only do 2 heating rounds and my differences here are not any different. It looks really good to me. That means you're at constant weight, or by the definition of constant weight. Not necessarily constant. It's changed. It's less than 0.0005 though, and that's all that matters. So maybe 2 rounds is all you need. And if so, great. Good for you. I mean, but if you're unlucky, then round 3, round 4, round 5, round 6, round 7, round 8, round 9, who knows how many hours you have to sink into these heating periods in order to get these to match and meet that definition. So in our lab, for us, what we will do on this day is we will do 1 round of heating. That is it. We're not going to do a second round. So we're not going to check to make sure that these numbers are really close together. We just don't have the time to do that. But I need you to understand that that is something that is done in real life. It is a half 2 round 2, because it says dry the sample for 1 hour at 180, cool, repeat the drying cycle. So round number 2 is at least a must. It is a have to. You have to do it. So you got to do round number 2 no matter what. Now, if we have the time, we might squeeze it in. But most of the time, it's just us giving you the idea of the process that has to happen, and then you walking away understanding that you repeat that process time and time and time again until you get a constant number, because that is what this method asks for, and that is what we need to be generating. So multiple heating rounds will always be required. Always, always, always be required. You got to do this at least twice. But in our lab, we're going to do 1 round of heating, we cool it, and then we take a mass, and they're going to base our calculations off of that first mass that we obtained. Folks, we only have you for a certain limited amount of time. We don't have you all day. You're not working an 8-hour shift, and you're not coming in the very next day to pick it all up and do it all over again. So because of that, we've got to kind of make some exceptions, and this is one of the exceptions that we do. Next up, calculations, section 8. So it says, in order to calculate the filterable residue, you're going to do the following, and it gives you A minus B times 1,000 divided by C. Okay, well, that's good. All right, so this allows me not to worry about like, oh, okay, well, what kind of stoichiometry or mole ratios do I need to bring in to the calculation? That's not what this is. It is just, here's the numbers, and this is where they go, and we're going to solve. And if you got a spreadsheet, well, guess what? The spreadsheet very often will do these calculations for you because the company doesn't trust you to do the calculations for you. They will do it, and they will do it in form of a spreadsheet that you will go into and key in a value, and then and that number just kind of pops up on the spreadsheet. We are going to give you a spreadsheet. We are going to tell you to fill in data, but we're going to get you to do the calculation yourself in the spreadsheet. Our spreadsheet versions that we give you will not be the you're going to have to be a little bit more manual than that because we want you to get really comfortable with Excel, how to key in calculations and do things for yourself. So it will be similar, but all of the information is going to be there, and then you can use that to calculate your own thing. So in order to calculate this stuff, it looks like I'm going to take the weight of the dried residue plus the dish in milligram. All right, so keep in mind, our balances are measuring in grams. So in order to get to milligram, you need to multiply by 1,000. That is how we go from gram to milligram. So whatever value that you get on our balances gram-wise, you need to multiply by 1,000 in order to get that into milligram. It is the milligram that's going to go in here for A, and this is the dish plus the residue. If you visually see that residue, okay, you visually see it. It's that residue that is left behind. So that will be the greater number, of course, all right? And then we're going to subtract that from B, and B is the weight of the dish in milligram. So this is just the dish only. That is it. So the clean dish has a certain mass, and then the dish and the residue has a certain mass. So in order to calculate the mass of the residue, of course, you just take the difference between those two numbers, and that's why there's a subtraction in here. So the dish and the residue total minus the dish only will give you the amount of residue that you have generated, that you've captured, that you have in that evaporating dish, all right? So again, it's got to be milligram, multiply by 1,000. That way you can start those two numbers together. Next up, we're going to multiply by 1,000 up here at the top. Please do this first. That needs to be done together in kind of separate. Do not automatically just hit divide by C, because sometimes it will only take 1,000 divided by C, and that is it. The order of operations is not fulfilled. So do the top piece first and get a number for the top piece, and then divide that by C, and C is the volume of sample that is used in terms of milliliter. And you should be using 100 milliliters because that is what the method told you to do. So you're going to take the residue amount in terms of milligram, and then you are going to divide that by the volume of sample used in milliliter. All right. So the number in milligrams of residues times 1,000, and then you're going to divide that by the volume of sample in milliliter. All right, so that's how we do the calculation. Very straightforward. Do it in baby steps. So do the subtraction first, then multiply by 1,000 to get a number, and then divide by C, which is the milliliter. And what this is milligram per liter. And that milligram per liter of course, is part per million. That is what that unit represents. And now you're looking at this and going, but Tracy, I thought you said part per million's milligram per liter, and we're dividing by C, and C is in milliliter. Wow, why are you doing this to us? Well, the built-in conversion here, and one of the reasons that 1,000 is there, is to take care of that. So we are self-correcting ourselves in the equation. So that way you're not necessarily taking the milligram divided by the liter. We're trying to give you an equation. That equation's using numbers that you have generated. That equation could look something different. I mean, I don't need milligrams on top. I can do grams instead. If I did grams on top, then I need to make sure that I do liter on the bottom and not milliliter. But that's kind of how this equation is just made. So it is self-correcting for those. And when you key in your numbers into that equation, it self-corrects for that unit. So that number that you're going to be popping out and generating in that equation, ta-da! It is milligram per liter in the very, very end. And that is also called part per million. Section 9 is accuracy and precision, and it just says, oh, this is not available at this time. And then finally, your references here that the EPA has used to generate this method with will be listed on the second page of method 160.1. All right. So that's the story with method 160.1. Again, this is total dissolved solids, and it's the idea that I've got a sample with some stuff on the inside that has been dissolved. I'm going to pour it through some type of filter system, and that filter system is going to collect that sample, and I'm going to take that sample, I'm going to evaporate that water, and I'm going to look at how much residue is left behind. That is total dissolved solids, otherwise known as filterable residue. All right. So in the next video, we're going to talk about total, something that else is not TDS, but TSS, and that is total suspended solids. And we're going to see how that one's different, and maybe how these two are really connected together. If you do one, you're going to kind of be doing the other one at the same time. So you can talk about them as separate methods, and you can talk about different data that's associated with them. And that's what we'll pick up on, and that's what we'll discuss in the next video.